Recording now. Thank you, Andrew. If I change it to be, whoops, I want alpha. Let me reload that. I want alpha to be 2 right here. So I'm just messing. These are parameters you can use that there's some. I think it's some sort of distribution that you can move around alpha and beta, and this line moves. And the idea is that the area is always going to be 1, so you can play around with it and get different shapes. But now, instead of a sample size of 2, let's make it a sample size of, let's say, the maximum 15. Can anyone predict how the bell curve, how it's falling here, how it would compare to the bell curve that we get over here? What do you guys think? So this one, it rains 15 droplets from the cloud, 15 at a time, and it records that number. Gabby suggested that there will be more columns and the columns will be smaller. I'm not sure if that would happen in this visualization. I would like to see that happen, but it might not necessarily happen. But there is something that will be a little bit, there is something that will change, and I think you're kind of going in that direction. What do you guys think? What happens, do you guys remember the formula we wrote for the central limit theorem? So not just more defined. So remember bell curves, they always have to have area 1, right? So what happens if sigma, the standard deviation of that bell curve, gets smaller? Because if you remember in the formula, in the central limit theorem, we said that the sigma for x bar, for the distribution of the average, becomes the original sigma, but divided by square root of n. Exactly. So if z gets smaller, then the curve becomes more compressed. Nice, Angel. So so do you guys see that if you make the, we kind of saw that when we were doing the, yes, exactly. When sigma gets smaller, the bell curve, as we saw in Desmos, got skinnier and skinnier and kind of had a peak closer to the mean, more concentrated at the average. And if you think about that, that kind of makes sense, right? If you take 15 things at a time, you're going to have a better estimate. Like most of the time, you're going to get the average of 15 things is going to be more accurate than the average of just 5 things from the cloud. So let's try this. I'm going to do it again. Do this again, and then let's do it a bunch of times. Keep doing it. Keep doing it. Keep doing it. Okay. Okay, just gonna hit it a bunch. Unfortunately, here the bars don't get thinner. That's just the way they set it up. But you could, if you visualize the bars getting thinner, you'd see that it starts to look really nice. And this is what the central limit theorem predicts. And look at that, it fits pretty well. It would fit even better if we had a really narrow, sorry, if we made the histograms have tinier intervals. It would fit really good. Now compared to this one, I do the theoretical. Do you guys see the difference between this one and this one? So that's the idea. As you increase your sample size, the theoretical distribution of the sample mean gets narrower. And what I want to do today is demonstrate, at least to understand why it goes like sigma divided by the square root of n. We're going to use that formula a bunch. Maybe I'll even do a problem right now just to show you how to use it. And then I'll try to explain why is it square root of n? Why isn't it cube root of n? Why isn't it n squared, or why isn't it just n? We don't have a chance to explain why the bell curve shows up. Why does it happen to be a bell curve? That's you need to take a later course for that. But we can explain why 1 over root n shows up for the standard deviation. So let's do a problem together. It's kind of like a review for the homework, and then we will talk about kind of why it's happening. So let me pull this up. Stop share. Okay. 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 So this is going to be for not this coming homework, but a lot of the main idea of what we're going to do next. So so applying the central limit theorem. And we're going to do this next time as well. And you'll see it's really essentially what we already learned, but just one extra step. That's it. You'll see. So applying the central limit theorem to answer questions about the distribution of sample mean x bar. We also call this the sampling distribution. So if you ever hear these terms, they mean the same thing. So anytime you hear distribution of the sample mean or the sampling distribution, those are the same thing that people are talking about. Okay, so the central limit theorem says that if you have a bunch of independent and identical distributions that you're drawing from, so like that cloud that we have, that's the distribution, right? And we keep taking draws from there. So if you draw a sample of size n from distribution, and this could be any shape. That's the idea, right? Any shape at all. We have no information about it. That's the really powerful thing about central limit theorem, is we have no idea what we're picking from. We didn't need to know to talk about that theoretical bell curve. We didn't need to know what the cloud looked like. We knew just based on how many times we're drawing what that bell curve is going to look like. We need to know a little bit about it, but not the entire shape. If you draw from a distribution with mean or with expected value, with expected value mu and standard deviation sigma, then X bar has the same distribution as the normal distribution with mean still mu, but now the standard deviation is no longer sigma, but it happens to be sigma over square root of n. Okay, so let's see this in action. We did some problems previously about elephants, so let's just stick with that. So assume elephants, all elephants in the world have a mean of let's say 12,000 pounds and a standard deviation of 2,000 pounds. Now it happens that this is also distributed like a bell curve. It doesn't have to be, but we just need to know these facts, that there's an average. We need to know the average, the expected value, and we need to know the standard deviation. And keep in mind, every sort of distribution, every cloud, not just the bell curve, every distribution you can think of, you can calculate these numbers. Okay, so we took a sample. We take a sample, a random sample of 25 elephants. And calculate X bar. So it's the average of 25 elephants. The question is, what is the probability, or find, and I'll just do a simple one. Find the probability, what's the chance that the average of the 25 elephants that you found is less than 12,200? So I'm just going to pause here for a moment. Do you guys have any questions about the statement, any confusion, anything like you want to ask, or any argument you want to say, hey, I don't think this makes sense, or why are you asking it like this? Any questions at all? It's a great time to ask. Let me ask a conceptual question that if you understood the statement and kind of what I'm talking about, you could answer this without doing any math, okay? What do you guys think is bigger? This quantity that we're looking for, the chance that the average of 25 elephants is less than 12,200 pounds, or the chance that a single elephant is less than 12,200 pounds. Which one is bigger? What do you guys think? Hit A if you think the left one is bigger, and B if you think the right one is bigger. Or no if you have no idea. Yeah, okay, let me repeat the question. So this thing that I want to calculate this thing. This is the probability that the average of the 25 elephants is less than 12,200. This one is the probability that the average of a single elephant is less than 12,200. So the question is, which one do you think is bigger? The chance that a single elephant is less than some weight, or the chance that the average of 12 uh, of uh, okay, yeah, I'll get a few more votes. I got a bunch of votes for the right one, that this one is bigger, and I got a little bit of votes for this one. So let's get some more votes going. Okay, anyone feel like they can argue their case? And totally take a stab at it. You can be wrong, it doesn't matter. Looks like you guys are broken up 50-50, which is good. Who wants to argue? Any volunteers to argue for this case?
I could argue the left if you want.
Yeah, go ahead.
So the reason I put the left because for multiple elephants, you're gonna get a bunch of different like sizes. So compared to just one,
right?
When you average them up, it's probably gonna be bigger.
Oh, well, what about the probability? What about you're definitely right. You're gonna get more variety when you get 25 elephants. But why does that make it more likely that you'll observe the average to be less than 12,200?
Because the mean's 12,000.
The mean is 12,000. That's true. The mean is 12,000 in both cases. But let's go back. Let me just share something.
Yes. Remember, like when we were doing the data set for like the dice rolling, the expected value was actually higher than the average. I'm still not entirely sure why, but I've seen other examples in that, so I think it could be a case for 12,200.
Andrew, what did you mean by the expected value is greater than the average?
I mean, I'm not entirely sure if that applies here, but like when you were saying, when we were learning expected value a few weeks ago, like if you averaged out a dice roll, typically you would expect 3 to be the average because 3 would be like the middle, but it's not. It's 3.5. Well, no, 3.5 is the middle, isn't it?
Yeah, 3.5. Yeah. So there's nothing changes when you take a sample versus just taking one thing at a time. It turns out that actually nothing changes with the middle. That's a nice thing. Like the middle is always going to stay the middle. That never changes. So 12,000 is, by the way, okay, this is the first question, another good reality check on both of these. Is this number greater than 50% or less than 50%? What do you guys think?
It's greater, right?
It's greater because it's to the right. We're talking about the chance that an elephant is less than 12,200, but the middle of the distribution is 12,000. So, and we know that like weights and things are generally bell curves. So we can say that this is going to be greater than 50%. This is also going to be greater than 50% because the middle of this one, X bar, the middle of like that where it can fall is also 12,000. So this is also bigger than 50%. Yeah, Archer, I think you're on the right track. What did you say there?
I said I think the chance that the percentage chance for the left one is greater than the right.
And what do you? I like your comment there. Bigger sample size, so stricter average. What do you mean by that?
Because of the fact, like exactly what you were showing with all the like having the max sample size and like constantly clicking it, it made that middle average be so strict. While of course there were some that fell like around it, it usually fell very close to that complete average.
You got it, exactly. So just to kind of give you a picture of the bell curves, that this bell curve, a single bell thing, you know, it's distributed like this. So this would be 12,000, and then most of the things are from like 10,000 to 14,000. That will capture most of the data. But we saw that when we took a larger sample size, each time we do that, each time we take a sample of 25 elephants, it made it much more accurate to be, it made it the X bar, it's still a random thing, but it always fell a lot closer to 12,000. So it's a skinnier bell curve. So it looks kind of like that, right? So the chance that you're going to be to the left, and both of these bell curves have area 1, right? But the chance here is a little bit over 50%. If this is 12,200, let's say. But the chance here, because it's a steeper bell curve, and I guess it's not the most convincing picture, but maybe if I draw it like, it's probably a little bit more like, go back. I don't know how to go forward, but there's 12,200. There's, let's say, 14,000. So, it's probably going to be more like that. Here's 10,000. And here's 12,200. It's going to look like this. So, and this is not to scale. Honestly, it would probably be even steeper, but I just don't want to go because they both have to have the same, both have to have area 1. So maybe if I kind of draw them on top of each other, it would be clearer. But, here, so it'd be kind of like, honestly, it would be kind of like this. Something like that. Okay. So you could say that this is, and it tapers off much more. Okay, so let's actually calculate it to see why that's the case. But how does that for the intuition? Does that intuition make sense?
I have a question.
Yeah.
Sorry, I know you showed it in the visual representation, but I still don't quite understand why one of them has a much steeper curve than the other. Okay,
very good question. So the reason is because as we take a larger sample, we get more, the X bar has a much narrower distribution. The distribution of X bar, the sigma for X bar becomes the original sigma divided by the square root of n. And whenever you make the standard deviation of a bell curve smaller, it makes the bell curve itself much more narrow. And that's just a way of saying, if you think about if you have a really narrow bell curve, it's saying that most of the data falls really, really close to the actual average.
Got it, that makes sense. Thank you.
Awesome. And so it's pretty intuitive that would happen, right? If you take 100 elephants and you weigh them all and take the average, you would pretty much expect that that's pretty close to the average. Exactly. Angel made a good. More samples means you get closer to the average, like we were told a while ago. That's a pretty intuitive idea. What I want to show later at the end of today is why is it divided by square root of n? Why isn't it divided by n, or this square root of n turns out to play a major important factor. So I want to kind of go into that later. But now let's just do this problem. So this was just a little digression, so you have some intuition on what we're about to do. The rest of it is really just really, really simple. It's literally what we did earlier, but just different numbers. So all we need to do is plug into this formula. So the last standard deviation was 2000, the original. The new standard deviation, you can write it as sigma x bar, sigma sub x bar. So the standard deviation for the sampling distribution is sigma, the original, over square root of n. And so I'm going to just punch it in, 2000 divided by the square root of 25. And that's going to be 2000 over 5. And so this is just 400. So the sample mean of 25 elephants is distributed. That tells us that the sample mean, x bar, is distributed like the normal distribution that's centered around 12,000, but has a standard deviation 400. Well, now we can answer this question because we know how to. If you ask me what's the chance that it's less than 12,200, and I know the mean and I know the standard deviation, I can answer that. So let's find the z-score. The z-score of this is equal to x minus mu over sigma. And this is, maybe I'm not going to write this up. X, mu, and sigma, you have to be careful because they're just general terms. So there's sigma x sub x bar, and there's sigma of the original one. So in this case, we're using this as our sigma. But once everything, now I think of this as my mu, and this is my sigma, I can forget about everything I just did. So I'm just going to count the number of standard deviations away I am from the average. So it's 12,200. 12,200 minus 12,000 divided by 400. This tells me that my z-score is 0.5. So what I'm really asking when I'm asking this question is I'm asking what is the probability that I observe a z-value that's less than 0.5? And then I just have to look that up in the table. So z-score less than 0.5. You guys can try that out on the z-table. And let me know what you find. I'm going to do it as well here. Z-table. So Angel, the standard, very good question. The standard deviation changes because we're no longer talking about the distribution of a single elephant. Like if I get a single elephant, right, it's not totally weird for me to find that it's not totally weird if I pick a single elephant to find that I get one elephant that's like 9,000 pounds. What do you think about that, Angel? Like, is that, it'll be a little bit low, underweight, but like that could happen, right? But if I take, like, let's say instead of 25 elephants, I do even more, like 100 elephants. If I take 100 elephants, a sample of 100 elephants, now it will be much weirder for me to observe that the sample average of 100 elephants is 9,000. That would mean I did something wrong, or for somehow, like, it could happen, definitely could happen, but it seems very, very unlikely, like intuitively, that would happen. You would need to pick a bunch of underweight elephants by chance. And if they're already rare, then the chance that you pick 100 of them that are rare is even lower. So in general, as we increase the sample size, the distribution of X bar has a tighter and tighter, smaller standard deviation. And then Aiden, nice, okay, good. This is just looking up at point, if you look at 0.5, point is going to 0.50, 0.6915. Okay. All right. Angel, did that answer your question? So this is what I really like about this. If you understood the last topic where we did the stuff with the bell curve, the only thing you need to know to answer these types of questions, there's only one thing you need to know. You need to know that the standard deviation that you're going to work with is no longer the original standard deviation for one element of this distribution that you're picking from, but it's that original standard deviation divided by the square root of n. And the rest of it, you can forget about everything and just do the problem as you're doing a normal bell curve problem. So that's what I really like about it, because once you see that formula, and you can just, you know how to do it already. This is a tiny difference. Okay, let's discuss a little bit. So that's how you do these problems. We're going to do more of them next week and talk about some ideas behind these, but that's pretty much it. How do you guys feel about this example? Do you guys agree that this is really easy if you understood the last, if you found the last part like straightforward and that just plugging in to get root n, but you do need to know how to interpret z tables and stuff. And in fact, like I said, once you understand z tables, to apply statistics, most of it is just knowing like the right formula to use for sigma. Different situations, you're gonna calculate sigma a little bit differently. But once you calculate your sigma, then you do the same thing over and over, pretty much. Okay, so let's discuss a little bit theoretically why the heck there's a square root of n. Because I think that to me was always a little mysterious. And it's not too hard to see why. I think it's a worthwhile thing to do. Let's see if we can at least get to it a little bit. So, okay. So what we're going to talk about now is this idea of how does variance change when you scale a random variable. So recall that variance is just the square of the standard deviation, right? In standard deviation, actually, you first calculate that variance and then you square. So, so just recall that the way to calculate variance for a discrete random variable, so going back to dice rolls, which I like a lot because it's a easy example to understand and we can calculate it pretty nicely. So we have x, p of x, and we have 1, 2, 3, 4, 5, 6. And then we have everything is 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6. And also this is a fun experiment to try out as well in the spreadsheet. And to calculate the variance, you recall, we have to do a new column here, x minus 3.5, or mu, squared. And then to calculate the variance, we're going to put numbers in here, each of these for x, and square it. So it would be, this would be a negative 2.5 squared. This one would be negative 1.5 squared. This would be negative 0.5 squared. This would be 0.5 squared. This would be 1.5 squared, and this is 2.5 squared. Okay. So to get the variance here, I just have to multiply this number, this quantity times the weight, 1/6, this times 1/6, and then add them all together. Thumbs up if you remember this from the spreadsheet and how to do this. Anyone, any questions about this? Good. Okay. So now my question is that I want to study is what happens if we scale the random variable, meaning that instead of using 1 through 6, we multiply all of the numbers by 3, let's say. So now the dice are going to change by 3, by a factor of 3. So if I change this to be 3, 6, 9, 12, 15, and 18, right? This is the distribution for this was x, and let's say I'm going to call this now a new random variable. Let's call it y. It's a little y, and we're going to say capital Y is just 3 times the original x. the probability of it doesn't change. If it's still a dice, everything is still 1/6, 1/6, you know, over and over. 1/6, 1/6. So here, the expected value of x was 3.5. What do you guys think is the expected value of y? Has that changed? And what is it? Nice. Nice, Archer. I agree. It definitely has changed. And what would it be? Nice. Again, and how do you get 10.5? What's the easy way to get it?
You add up all the variables and you divide by the n.
Exactly. But in particular, if we just multiply every outcome by 3, how would that affect our average? It would also multiply by 3. Right? So this is exactly going to be, the new one is 10.5. So it was 3 times the previous one. But now is where it gets interesting. And it's not too difficult. But this, what should I do here if I'm going to write y? But now it's no longer minus 3.5. Now it's y minus 10.5 squared. So instead of negative 2.5, when I plug in 3 for y, I'll get negative 7.5 squared. And over here, I'll get 6 minus 10.5 is negative 4.5 squared. And here it'll be negative 1.5 squared. And over here, it'll be 1.5 squared. And here it'll be 4.5 squared. And over here, it will be 2.5 squared. Oh, sorry, not 2.5, 7.5 squared. So what do you guys think will happen to the variance? By the way, I forgot, what was the variance? Does anyone remember? I'm just going to look it up on the Google Sheets that I had. I shared. And I'll show you, we can see this exactly in a second. So the variance of the dice roll, this was from the spreadsheet, it was 2.92. What do you guys think will be the new variance of the dice roll, but the dice no longer is 1 to 6, it's 3 to 18? Based on what we're seeing here, anyone want to take a guess what it would be? There's just a little bit of algebra to see there, just kind of a little bit of, anyone want to venture? So the expected value of y tripled. Okay, I don't think it's 11.6 as the, well, hang on. I don't think it's 11.6 as the variance. So it tripled, I'll give you a hint. It tripled from here to here. And that's because all of these numbers tripled, right? Went from 1 to 3. But to get the expectation value, just multiply by 1/6. But this amount got tripled. This amount got tripled. This, everything got tripled. So the whole thing got tripled. So what do you think would happen to the variance? Keep in mind, the variance used to be this number squared, negative 2.5 squared, times 1/6. But how does this number, negative 2.5 squared, compare to negative 7.5 squared? Which one is, how many times bigger is this number compared to this number? And this is something we talked about in algebra a little bit. Angel, very good. Is it actually 3 times bigger? and this is where it's tricky, right? This number, negative 2.5, and negative 7.5 is 3 times bigger than negative 2.5. But what are we doing after we calculate the number inside of the parentheses? We're squaring it. So this has a factor of 3. The inside is 3 times bigger. But if you square something that's 3 times bigger, how many times bigger are you actually making it? It's 9 times bigger. If I have a little square, just to kind of show you, this is the idea, and one of my favorite ideas in math. It's so simple too, but really, really powerful. If you have a little tiny square and you triple the side length of the square, the new area is equal to 9 times the old area. Exactly. So the new variance is equal to 3 squared times 2.92, and that's roughly 26.28. That's Angel, correct. The volume would change by the cube. That's right. Okay, and now I'm just going to put the formula down here. So, by the way, to understand that this happens anytime you anytime that you take the anytime you multiply a random variable by a constant, you scale it. It's not hard to see why this happens. It's not particular for the dice roll. It'll happen anytime because it's clear that if you just change all these numbers by a constant, the expected value will move by the same constant. And then in this expression, everything gets changed by that same constant inside, but the variance involves squaring it. These never change, but this is going to be multiplied by the square of your scaling factor. So in particular, it tells us something about the standard deviation. So whereas the old standard deviation, this is from the spreadsheet that I shared with you guys. I'll show you in a second also how it works. 1.71, this is the old standard deviation. How would the new standard deviation change? What happens if you take the square root of this number? What would the square root of this number be? This was the square root of 2.92. Nice. Angel, you're perfect. Angel wrote 3, because you take the square root of the top, you get 3 times the square root of 2.92. And so it's just going to be 3 times 1.71, which, just look that up, 3 times 1.71 is 5.13. So here's the moral of the story that's really nice. And I'm going to write sigma for the, just to make it not confusing, sigma of the standard deviation of the x distribution is 1.71, but the standard deviation of the y distribution is triple that number. So that's the keys, that variance based on the formula will change by the square, and the standard deviation, because the square root of variance just changes by a constant amount. The original scaled amount, because it's the square. Let's see, I wrote it down previously very nicely. Okay, so I'm going to just summarize this result. Variance of n times x is equal to n squared times the variance of x. That's what we just observed. And it's not hard to believe why this is true. Just based on how you calculate variance, and n squared pops out. And similarly, the standard deviation of nx, well, it's the square root of the thing above. So that just becomes n times the original standard deviation. So we're very close now. Now let's ask a question. And I alluded to this before, that if you just triple the dice value, one way to interpret that is as if you're drawing, you draw one dice, but you're lazy. Instead of doing like drawing 3 dice, you just write down the same answer you got 3 times. But instead of doing that, imagine you actually draw the 3 different dice, or you roll the dice 3 times, and you get a bunch of different numbers. So what about, so what about drawing from x n times and no, sorry, with replacement. So each time is identical. Each time is independent of the last, independent of the previous. So you just roll the dice 3 times or n times. In this case, y is no longer going to be 3x, but y is a little bit different. Y is going to be equal to x1 plus x2 plus x3. If n equals 3, this is in the case n equals 3. Do you guys see how this is different, just to kind of note, versus what we talked about earlier? We had y is equal to x1 times 3. So it's the same outcome added 3 times. That's how you can interpret it. Versus this is 3 dice. And we discussed this before, because we discussed a version where there's 2 dice being added. And the outcomes ranged from 2 to 12, and you could actually get 3, because you could get like the first one is 1, the second one is 2. So it turns out that when you calculate the variance of this expression, because these are individual and independent variables, it turns out that the variance in this case is equal to the variance of x1 plus the variance of x2 plus the variance of x3. And because all of these are the same distribution, we no longer have a 9, but we have just a simple 3 in front of the variance. And I said that without proof here. And so this statement, involves a little bit of algebra to show it, but you can start to, you can start to believe it. And I want you guys to try this as an extra credit, okay? And I mentioned this in the homework. See if you can do this over the weekend. And it's actually it's not going to be hard to do, but it's worthwhile to mess around with it. If you draw out that table that gives the distribution for x1 plus x2, so x1 and x2 are dice rolls or die rolls, we can make a table to calculate the probability of the distribution of y is equal to x1 plus x2, which is the sum. And we saw that y, the chance of getting a 2 is 1 out of 36, right? The chance of getting, here, 1, 2, 3, 4, 5, 6. So there's 36 different, the sample spaces, there's 36 different outcomes, 1, 2, 3, 4, 5. The chance of getting a 3 is 2 out of 36. You can get a 4. 3 out of 36, you can get a 5 like this, and so forth. And the last one will be a 12. So 1, 2, 3, 4, 5, 6. So you could make on Google, on the Google Sheets, and I encourage you to do this, see if you can find out the variance of x1 plus the variance of just of the sum of 2 dice. Sum of 2 dice. And that just involves making a slightly bigger table on Google Sheets. And it's no longer the outcomes are going to be, the table is going to be y, p of y. And I'll just set you up for the first one. The lowest y you can get is 2, and the chance of observing that is 1 out of 36. The next one would be a 3, and the chance of observing that is 2 out of 36. So just keep doing that all the way until 12. That's the highest thing you can observe, and the chance of that one is also 1 out of 36. And then calculate the variance, and if you have the table set up, it does it automatically. Yeah, see what you get when you find this variance, and it should be related to this, or to this kind of pattern. And so so this is the key concept, is that if you do the same thing, like the actual same outcome, and just record it a multiple number of times, or you just scale your original random variable by n, you get an n squared that pops out. But if instead of doing that, you're adding up n identical to outcomes, sorry, if you're adding up n different outcomes, but coming from identical distributions, your random variable only multiplies by, the variance only multiplies by that n. And here's the kicker, and I'll just mention it. This, by the way, this homework, it's not going to take too long to do it. I'll show you also on Tuesday, but yeah, it's focus on the Khan Academy stuff. If you have time and you're curious, I encourage you to mess around with this. But yeah, just focus on the Khan Academy. It was just extra credit, or just a little extra challenge to miss. Now let's look at what the variance is. So this is, now we have everything we need to know, everything we need to explain why there's a sigma over root n. So x bar is equal to x1 plus x2 xn. And let me do it like this. The random variable x bar comes from x1, x2, x3, all the way to xn. But you don't just add them together, you also at the end divide it all by the number n. And n is just a fixed number. Now, if you want to take the variance of both sides, the variance of this, take the variance of this whole thing. Well, we know that this is just a random variable. And this is like a number. This makes the random variable that we are going to observe, the sum of a bunch of things, it makes it smaller by dividing by n. But we know that dividing by n is the same as multiplying by 1 over n. So what that's going to do is it's going to pull out a factor of 1 over n squared, 1 over n squared times the variance of x1 plus x2 plus x3 xn. Did you guys follow this step? That why I took this number out and made it 1 over n squared? The factoring, the reason this is like 1 over n, right? The reason I'd make it 1 over n squared is because what I showed you earlier about this. Whenever you multiply a random variable inside of the variance by some number, to take it outside, to get rid of that number, it gets squared on the outside of the variance. So whenever you just scale some random variable by a constant, you can take the constant out, but you have to square it. Does that explain? Are you guys okay now with why? So this is just the expression for the sample mean. This is a bunch of things added together divided by n. But to take the n out, you know, it doesn't look like before I had like 3 times something that maybe became a 9, but now it's 1 over n. But when I take it out, it's 1 over n squared. And the variance of n draws from the random variable. I didn't prove this, but we can mention something a little bit about it. And n independent draws, this turns out to be not n squared times the variance, but just the simple n. So this is equal to 1 over n squared times n times the variance of, let's say, x1, you know, because they all have the same distribution. And now 1 over n squared times n, well, the n's cancel and you're just left with the variance of x1 divided by n. And now, to get the standard deviation, we have to take the square root of both sides. So the sigma of x bar is equal to the square root of the variance of x bar, which is equal to the square root of the variance of x1 over n, which is equal to sigma x, or x1 if you want, whatever. I'll just do x. X, they're all the same. They're all some random points. But now the denominator becomes over root. So that's pretty much it. And I think it's really fascinating because it's all about scaling, right? It's the fact that when you multiply, you get the square, but when you add the independent random variables, you don't get the square. And when you take the sample mean, you're dividing by n, so that's why 1 over n squared pops out, but the numerator only gets an n, so the denominator has an extra n. So the variance has just an n sitting there in the denominator. And when you take the standard deviation, that's why you get it. You got to take the square root, so you have a square root of n showing up in this bound. So one thing that I glossed over is, why can we do this? Why is it that the variance of independent random variables is equal to n times the variance of, these are all identical, like identically distributed. why is it equal to just n times each of their variances? Or like just add, why can't you just add up all of their variances separately? And the reason for that really boils down to the multiplication rule. Yeah, so I'll let you investigate that a little bit, but that's kind of the overview of why a root n shows up in the denominator. And that way you know you're not just doing some formula. And I encourage you to think about this. It took me a while to understand what is not that difficult, but there's a bit of like interpretation to sit and think about what's happening here. And you can think about it later, like in the future as well. But just know that it's worthwhile to understand why a root n shows up in the sampling distribution. All right, guys, that's all I have for today. Do you guys have any questions? How many of you, just kind of thumbs up, and it's okay if you didn't. How many of you feel like you kind of understood this last part where when I go from here to here? And thumbs down if you're still pretty confused. Okay, we got a little bit. Any thumbs down? Any parts where I could clarify? And I'm not gonna ask about this or anything. This is just to explain, so you have an understanding of why it's true. You just need to know. The only thing I do expect you to know is the actual formula. That this standard deviation is equal to the original divided by root n. That's all you actually need to know. Okay, I will see you guys on Tuesday. Try out the, if you have time, please complete your homeworks. By the way, I can see like if you're doing the homework, I changed the homework due date from tomorrow to be due on Sunday. So you have a little bit extra time to try it out, to work on it. But yeah, tell like I see only like not too many people are attending class, so make sure that whoever, if you have some friends who are not coming to class or just getting notes, make sure they know that I can see like who's working on the homework, how much time they're putting in, and I see some of you are putting in a lot of hours on the homework, which is awesome. So make sure you actually do it. It's worthwhile. If you can't do some problems, that's obviously okay.
Is that if you signed in for your Khan Academy?
Mhm.
So I didn't actually do that, and I'm using my own Khan Academy account, and I'm like copying and pasting.
Oh, okay, that's fine. Yeah, just let me know if that's the case. Just email me if you're doing something like that.
Okay, cool.
And then I can also add you I can add your personal account to the.
That's true. I can also like pull up my Khan Academy and have the activity there if you want to check.
Yeah, that's perfect. Or yeah, just send me the email that you use with your Khan Academy, and I'll invite you to join the class.
Okay, cool. Thank you.
Okay, so I'll see you guys on Tuesday.
Have a great rest of your day.
Have
Oh,
a
yeah.
great rest of
Enjoy
your
week.
day. Thank you.
You too. And Brandon, sorry, the homework is due on I think I changed it to Monday.
Bye. Thank you.
Bye. Bye, Gabby.
Hi, I just had a quick question. This is very unrelated to what we did today, but just kind of I'm trying to study and get ready for the finals, and I was just wondering, will there be a practice test when we get closer to the date?
Yes, definitely.
Okay, perfect. That's all I had. And thank you so much for today's lesson.
Okay, for sure.
Okay, have a good day.
Okay, you too. Bye, Fiona.